Below are graphs of 4 exponential functions. Match each function with its graph. Notice that graph A is exponential decay, graph B is exponential growth, graph C is exponential decay, graph D is exponential growth. 2 of the graphs are decay and 2 of the graphs are growth. Notice also the y-intercepts of each of the graphs. Our scale, we're going from 0 to 30 along the y-axis. There are 1, 2, 3, 4, 5, 6 increments. 30 divided by 6 is 5. The scale is 5. So for graph A, there's a y-intercept of 5. Graph B, a y-intercept of 10. Graph C, a y-intercept of 5. And graph D, a y-intercept of 5. Now let's recall the form of an exponential function. Each of the given functions has the form a number times another number raised to the independent variable. So the form of an exponential function is a of x is equal to a constant c times the growth factor or decay factor a raised to the x. Now notice in this function that if we replace x with 0, we would get a to the 0 is 1 and 1 times c is c. When x is 0, the output is c. That means that c corresponds with the y-intercept of the graph. C is the y-intercept. Notice that only one graph has a y-intercept of 10 and only one of the equations has a c value of 10. So right away we can determine that graph B corresponds with R. In our exponential function, the a value is either the growth or decay factor. It depends on whether a is less than or more than 1. If a is a number that's less than 1, then we have exponential decay. If a is a number greater than 1, then we have exponential growth. If we look back at equation R, we have R is equal to 10 times 1.8 raised to the x. The y-intercept is 10. 1.8 is larger than 1, and notice that our graph is exponential growth. Well, only one other graph is exponential growth, so all we need to do is to look for the other equation that has a growth factor that is bigger than 1. For P, the growth factor is 0.7. That's less than 1. For P, the value of A is 0.7. That's less than 1, so that indicates exponential decay. For Q, A is equal to 0.4. That's also less than 1, so that indicates decay. For S, the A value is 3. That indicates exponential growth, so S corresponds with graph D. So we're down to P and Q. Both have a y-intercept of 5, and both of them represent exponential decay. So how did we distinguish one from the other? Well, we might try substituting different values for x. For example, with p is equal to 5 times 0.7 to the x, we might try substituting in 2 for x, since 2 is to the right on the x-axis, and also negative 2. So let's try substituting 2 for x in equation p. We get p is equal to 5 times 0.7 to the second power. Well, 7 times 7 is 49, so 0.7 times 0.7 is 0.49, which is about 1/2. So this is approximately half of 5, which would be 2.5. Also, if we substituted negative 2 for x, we would get p is equal to 5 times 0.7 to the negative 2. So again, 0.7 times 0.7, that's equal to 0.49, which is about 0.5 or 1/2. The negative exponent indicates that we need to take the reciprocal of that. The reciprocal of 1/2 is 2, and 5 times 2 is about, well, 5 times 2 is 10. The value of the expression is approximately 10. So what we want to do is to look for the graph that has the point 2, 2.5, and negative 2, 10 on it. If we go over 2, it's a little bit hard to tell exactly how high graph A is, but if we go over to negative 2, it looks like graph A is approximately 30 units high, but we only want it to be about 10 units high. So if we look at graph C and go 2 to the left and up, we see that it is approximately 10 units high, and so that allows us to determine that P corresponds with graph C. Okay, by default, that means that Q should correspond with graph A. Let's go to our calculator and check. We go to y equals and enter our Q function. We'll use y instead of Q. So y is equal to 5 times 0.4 raised to the x power. And then we want to create a good viewing window, so we go to Window, and we notice that along the x-axis we're going from negative 2 to 2. And the scale is 0.5. And for our y values, we're going from 0 to 35 with a scale of 5. And then we press graph, and we notice that our equation corresponds with graph A.